So we're talking about water can behave as an acid or base. So what if you have two molecules of water together reacting, one behaving as an acid, one behaving as a base? So you have a pseudo acid-base reaction. This guy behaving as an acid give off its H plus and becoming its conjugate base, the hydroxide, whereas the other one behave as a base. The base pick up the H plus from this guy and become a hydronium ion. So the acid dissociation constant for this equilibrium will be, likewise, you put it back into the equation here and you get this. And when you do some manipulation, you find that the product between the hydroxide ion and the hydronium ion, it becomes this value, which we call it Kw, the ionic product of water. Again, see, it's a big K, a form of equilibrium constant. This subscript here, W, indicates water. So you have a value of 1 times 10 power negative 14 for the ionic product constant of water at room temperature 25 degrees Celsius and 1 atm. And this has got to do with what we know last time. The pH scale ranges from 0 to 14. And what is the midpoint? The midpoint is 7. We know the pH 7 means neutrality. Water is neutral, but this is only true if you're having RTP. If you go to extremely high temperature or low temperature, then the neutrality point will change. It's no longer pH 7. So I cannot make a statement and say that any solution with pH 7 is neutral. That's a fallacy because you didn't tell me what are the external conditions. Now the concentration of water is 55.4 molar, capital M means mole per dm cube, at RTP. Okay, you do some math here and you get pKa equals to 15.74. Okay, we went through this one more time. Strong acid give off H plus very easily. Conjugate base is stable, it doesn't want to pick it up and go back to its undissociated form. And for weak acid, likewise, want to hold back its H plus, doesn't want to give up the H plus, and the conjugate base is super reactive, grab the H plus and go back. So strong acid will have a weak conjugate base, and weak acid will have a strong conjugate base. That's how it goes. Now let's do some exercise. Here, we're trying to predict the acid strengths from pKa values. We know that high Ka means low pKa. Low pKa means stronger acid. Now water has a pKa of 15.74, acetylene has a pKa of 25. Who has a lower pKa? Water. Lower pKa means high Ka. High Ka means more acidic. So this guy is more acidic. It means this guy will prefer to give off H plus compared to the acetylene. Got it? So now the third question is, does hydroxide ion react with acetylene? We went through this. We compared the pKa value, understand the terms, the translation between pKa, Ka, and strength of acid. Now to check whether the equation goes through, the answer is no. Because water is a stronger acid, so water prefers to give up H plus compared to the acetylene. So that means if you compare the stability of the conjugate base, the hydroxide, and the anion coming from the acetylene, who can stay there longer? Hydroxide. Because water, being the acid, is a stronger acid. So strong acid means weak conjugate base. Weak conjugate base means more stable, it can stay there. Acetylene, lousier acid, conjugate base is stronger. Stronger means doesn't want to stay here and stay there. So if we have this base that stay there that's not so reactive and the acid that's not so reactive, would they react? No. So coming back to biological sciences, most biological reactions involve organic acids and bases. So alcohol, vinegar, acetone. Some of these pK values that please do not memorize, okay? But you ought to know why vinegar is more acidic than alcohol. because it is a carboxylic acid. It says it's an acid. Acid must have a higher Ka and hence lower pKa than your corresponding alcohol. Let's go a bit deeper. Compare the strength of these acids, or behaving as acids. Alcohol, we always compare the stability of the conjugate base. So an alkoxide electron donating methyl group will increase electron density towards its O-, and hence the O- want to pick up an H+ and go back to stability. In your acetic acid, the conjugate base is the COO- with an alkyl group. Now your CO double bond is electron withdrawing, and you have an extra oxygen there that can pull electrons away from a negative charge. And on top of that, you have resonance form. The negative charge is split between the two oxygen. So at any point of time, you do not find a single negative charge on one of these oxygen, which means it's shed. It's thinner. It's not so concentrated. When the negative charge is not so concentrated, it cannot go and reach out to the H+ so easily. Now acetone could behave as an acid because after giving off its H+, it's able to form resonance form. You see the localization of the negative charge from the carbon to the oxygen. You can see from these electrostatic potential maps of the conjugate base of the methanol, vinegar, and your acetone. See that there's a high region that's in red, which means electrons of very high density, and it always hovers around the areas where oxygen is occupying the space. So you see that the electronegative oxygen atom stabilizes the negative charge in all three cases. Now carboxylic acids, they must contain a COOH group. This defines them. Vinegar, acetic acid, common name. Ethanoic acid, pyruvic acid, we have it in the body. Citric acid, same, and in the citrus fruits. Right. Now mind you, it doesn't mean that all the H's you find in any organic molecules are acidic. It doesn't mean that when you have H, you can give off H+. No. The one which is COOH could do it, definitely, because they are acid. The one that's connected to oxygen could also give off its H+. So you have to see the situation where this connects to. And most importantly, the rule of thumb is just to check the stability of the conjugate base. How are you going to stabilize it? Is it stable? Can it form resonance structure? Now coming to the bases. Bases, on the other hand, they like to grab H+. So these are some examples of bases: methylamine, methanol, acetone. You may ask me, hey, I thought you told me these are acidic. No, these are neutral. Alcohols are neutral, water is still neutral, acetone is neutral, but they can behave as an acid or base depending on the situation, the context. Now, amino acid, like the word suggests, amino means it has a amine group, acid means acidic functional group. It contains both sides, and they can form something called the zwitterion. 10 years ago, when I first learned about this zwitterion, oh wait, it's more than 10 years ago, long time ago, when I first learned about zwitterion, it sounds so cool, zwitterion, cute. And that was before the time where Twitter appears, but Twitter runs with Zwitter. So in alanine, one of the essential amino acids we find in the body that's uncharged, it will self-ionize. See this equilibrium arrow? It's longer to the right side. That means right, at any point of time, we find more of this form in the zwitterionic form compared to the uncharged form. Two reasons: because acid like to give off H+, and the base like to pick up H+. And on top of that, if you compare before, this is not just single molecule in the beaker or the vial that you have, it's millions of molecules, because a few moles, even millimole, you have a lot of them. Now before that, the primary forces of attraction between these molecules of alanine is only hydrogen bond. But after the self-dissociation, you have an ionic bond. And when we form something that's stronger, we form a bond that's stronger, we release energy. The process is exothermic. You are lowering the energy of the system, which means increasing in stability. Very favored, and hence is driven towards this side.